Here we go. So yesterday we talked about magnetic field, and I just want to mention a few things that are not usual, like magnetic field of Earth. We draw it like a uniform magnetic field. So they come out, field lines come out from southern hemisphere, which is actually magnetic north, right? So like this, and this is a magnetic south. However, magnetic field of Earth is not uniform. So I'm gonna actually write down. There are magnetic anomalies. So what are magnetic anomalies? We have places where there are rich deposits of iron ore. So iron ore, and specifically this configuration, is ferromagnetic. And what happens is that these deposits spontaneously magnetize. So it takes some time, but once it happens, any surrounding ore will also be magnetized, and this way it becomes like a permanent magnet deep underground. If using a compass in that area, the compass will go a little crazy because it will be showing you local strength of the magnetic field, not like average strength over the planet Earth. And if you know about it, you should not be confused. And instead of compass, you should use some other objects or some other items to find your location on the map, or figure out north and south based on observation of the sun or trees, or the stuff that usually is taught in Earth science. So there are multiple of these anomalies. I know since I grew up in the Soviet Union, we learned about the one near Kursk. If you heard about World War II, there was a huge tank battle near that town in Russia. And next by, they have huge deposits of iron ore that are still being developed today. I mean, they still get iron ore to make iron and steel. So that's what I know about that one. If you're curious, you can look them up. There are other anomalies around the world. I think there was at least one in Africa. I mentioned the strength of the magnetic field. So let's talk about the strength of the field. Let me see. We can go to this one. So I'm going to make the next slide. So we're going to have multiple slides. So the strength of the magnetic field is labeled B. Strength of magnetic field. Is B. It's a vector quantity. Now, obviously, I wonder why it's B. When electric field was studied, obviously it was called electric field, electricity, but magnetic field was not well understood until much later. And when people started coming up with formulas, they started with the first letter A, and there's some quantity A which will change over distance, and that change is gradient, and gradient becomes B. So that's, I think, what But this come from, if I'm wrong, I'm wrong. But that's how much I don't know about that. So B is strength, and the unit of B is called Tesla. Tesla, after Nicholas Tesla. And since it's named Tesla, Tesla lived in the 20th century. So you should understand that the naming and understanding of magnetic field came much later after people understood electric field. And there were many other people who contributed to magnetic field. There's another unit that is non-SI unit. This is SI unit. SI unit. There's another unit which is non-SI unit. It's called Gauss. Also mathematician, I think, Gauss. So Gauss will be equal to 10 to the negative 5 Tesla. Now, Tesla is a metric system unit. Gauss is non-metric. And the reason there's a huge difference between these two is kind of similar to Coulomb, right? Coulomb is a unit of charge. It's again part of the metric system, while like elementary charge or some other charges would be much smaller. Like on a daily basis, we don't deal with this kind of charges. We deal with static electricity. And to give you a sense of the strength of the magnetic field of Earth, actually, let me look it up. Hold on a second. Gauss. Tesla. Yep, I was wrong about the exponent, so let me just fix that thing. I knew there was something wrong about this. So exponent will be 10 to the negative 4 Tesla. So the field of Earth is about 5.5 Gauss. This is the magnetic field of Earth. So I can write B of Earth here. Now you should understand this is average value. Average value because it will vary from a little smaller value to a little bit larger value, and anomalies will give you a much greater number. Now I told you yesterday that magnetic field of Earth is quite weak compared to regular magnets that we're used to, but it's also enormous in size, so it reaches out thousands of kilometers into space. Now, how strong is Tesla? 1 Tesla magnet, if you have 2 magnets, if each of them producing 1 Tesla in their proximity, then these 2 magnets can actually, like if you put them on the opposite sides of your hand, they may actually break your bones. So those are very strong magnets, and neodymium magnets are among the strongest permanent magnets, right? And their strength can go, depending on the size, can go up to about 2 Tesla. So let me go to the, maybe I can write it here. So let me count that. So neodymium magnets, neodymium magnet. They can go up to 2 Tesla. 2 Tesla. So it'll be the size of your palm. The magnet will be about the size of your palm, and it will be really strong. You can look up, there's a website I think called Magnets for Less, and they have listed their with the Y here. Yes, I see. Thank you. So they will list the strength. Like for example, one magnet can lift 200 pounds. Basically, you can suspend something like a hovering chair or something, and then basically sit in the chair and not fall off the magnet. Now we have other objects. We have artificial magnets, electromagnets, which can go up to electromagnets. Someone's mic is on. Electromagnets. So the strongest electromagnets that were created on Earth are about 30, I think 30 Tesla, 30 to 40 Tesla. And you should understand this magnets are very temporary. So they create a really strong magnetic field, temporary, and then they have to switch it off. Otherwise, it will overheat. Electromagnet will overheat and will destroy itself. Solar magnetic field can be pretty strong. Let me see. So it could be around 1 Gauss, which is about 10,000 times more than the field of Earth, right? And near the sunspots, I think the field can go to about 1 or 2 Tesla. Now I forgot to mention the what's it called? Next slide. MRI, right? MRI machine. People call it MRI machine. It's actually an MRI because it's nuclear magnetic resonance imaging machine. But for some reason, people just like 3 letters. So this can create up to, I think, 3 Tesla. Depending on, again, it's temporary. It's not always that strong. Objects in space, which are considered to be the strongest magnets, are neutron stars. Neutron stars. And depending on the size of this, like, because they may come in different sizes. Let me look it up. So neutron star magnetic field. So they can be trillion of Gauss. Trillion of Gauss, we're talking about 10 to the 12. So that means it's about 10 to the 8 Tesla. Okay, so it's a very strong magnet, and there are some YouTube videos where scientists discuss like what would happen if neutron star would fly by, like around Jupiter's orbit or something, and some calculations show that like cars would fly off Earth and it will just fly towards the star. It's a very strong magnet, but you should also understand that magnetic strength drops inversely proportional to the cube of the distance. So over a large distance, we will not be able to feel that strength. Okay, so this is about different strength. Now, are there any questions before we move on to the formula? Question? No questions? Is E field in what is B field? Neutrons per something? Yeah, that's a good question. So B is actually, you will see the formula. I'm going to write the formula, and from there we can find the units. Okay. So we are not going this time. We're not going in the chronological order. So first, we're going to consider so-called Lorentz force. So Lorentz force Lorentz force. So basically, Lorentz was actually the first scientist who built particle accelerators. I believe he started as early as like the later 19th century. Lorentz force. Okay, so the formula looks like this. The force of the magnetic field, so I'm going to put B here, is proportional to the charge of electric charge, right, of a particle or something that is moving. The particle has to be moving, and it's a cross product. So we're going to talk a little bit about the cross product with the vector B. So if you want to find the units of the B, you should divide Newton by Coulomb and by meters per second. Okay, so if we try to like figure out the strength of the magnetic field by force, by charge, and by velocity. But then if you write it out as Q times, let's say, distance L and over time T, then the reason I'm using L is that it relates to the wires. Wires have length, and the wires also carry electric current. So we can write it then force divided by amp. Q over T will be amp. Actually, instead of amp, I should write current, and then second, time, right? Time. So then if we define the units for the B, this will be Newton by amp, divided by amp, divided by second. So that's the unit for the not second. Am I doing something wrong? Yes, I'm doing something wrong. Wrong. So this is going to be L, and this will be L. I did say L, and the last one will be actually meters. There you go. So that's the unit for the B, Tesla. So 1 Tesla, this will be 1 Tesla. 1 Tesla is equivalent to the strength of 1 Newton acting on a piece of wire which is 1 meter long that is carrying current 1 amp. So it may seem not a really strong field. It's just 1 Tesla, 1 Newton. But if you think of the amp, like amp is like 1 coulomb per second, right? So what we're looking at actually is the strength of the field created by the 1 meter long wire with the current of 1 amp. So this will be probably a proper way of saying it. Okay, so let's see, questions? No questions. Okay, so let's try to understand the cross product, and then after that we're going to talk about the right-hand rule. So let's see. Next slide. So cross product. So basically, if you have 2 vectors, so I'm going to try to draw it like this vector here, this vector here. We're going to call A, and we're going to call this B. If I want to find A cross B, I'm going to take vector A and rotate it towards B, like that. The longer the wire, the stronger the magnetic field. Yes, that's true, but the length of the wire is It's not like the long wire. It's like if you have, let's say, instead of one piece of 1 meter long wire, you have 10 pieces in the same place. So this way you have like either greater current or you multiply by the length. So that's how you can, multiply this. So that's the answer to Kyle's question. So A cross B, right? So we're gonna rotate A towards B. And what you do is you look at this as, let me see what we have here, highlighter. Think of this as a plane. That color. Go back. So rotate this way. And then maybe, I don't know, this one. So this will be like a plane. This is the plane. So think of these two vectors are in the same plane. And oh, come on. So, and let's see. Here. Right? And if you rotate A towards B, if you use like a screwdriver, then you will find that a screw will rotate in the direction from A to B, but its tip will move downward like that. So this will be the product. So let's call it C. Okay. So you can think of it again as a screwdriver. Let me draw a screwdriver. So basically we have a screwdriver. And then here we have the tip of the screwdriver, something like this. So if you rotate the screwdriver like this, right? Then the tip of the screwdriver will move down. Or if you have a screw, the screw here will move down. So if you have a screw here, like that, right? It will move down. Does it make sense? Okay, let's try another orientation. So let's say we have, if you screw the other way, it will go up. Yes, that's true. Let's actually look at the different configurations. So let's say we try two other vectors. So we're going to try this vector, assign this vector. And let's call this vector X. This will call the vector Y. Now these are vectors, but you will see resemblance with the Cartesian system. So we're gonna multiply X cross product. Let me just make it like cross product to the Y, right? So we're gonna rotate this then. We're gonna rotate this X towards Y. So as you can see, we're rotating now in the opposite direction as to the way we rotated the screwdriver. So if we do so, then let's see, the direction will be going this way, like that. And we can call Z vector, Z vector. And we end up with the XYZ coordinate system, which follows a very specific rule when you arrange the axes. It's called right-hand rule or right screw rule. And if you look at any kind of screw that you have around, like a screwdriver, like a regular screw, when you open the bottle, all the screws, they have the same orientation. They follow the right-hand. So like right-handed people will have easier time to open those bottles using a screwdriver. So I mentioned this before. Nature, for some reason, prefers right-hand rule over left-hand rule. And there may be correlation with what people have. I'm not sure if this is true for the animal world, but like people, like I think 10% of people are left-handed and the rest like right-handed. So whenever you draw XYZ coordinate system, it's always the same order: X towards Y, Y towards Z, Z towards X. So I'm going to go to the next slide. Are there any questions before we go on to the next slide? No questions. So we're going to do one more slide. Okay, so if I draw XYZ coordinate system, and this time is going to be orthogonal. Orthogonal means all the angles here are 90 degrees. Go back. So here you have 90, here you have 90, and here you have 90, right? X, Y, Z. And we cannot mix them up because they follow a very specific order. So as you turn X towards Y, you get Z. As you turn Y towards Z, think of a screwdriver, you're turning it from Y towards Z. And if you have a screw, like say in the screen, and you're turning the screw from Y towards Z, the screw will start coming out of the screen, and that will be the X-axis. And as you rotate Z towards X, you get the Y direction. So this is also called right-hand rule. And this is how you can understand this. There are different ways of doing this. I'm going to show you the way I'm more comfortable with, but you can look up the other ways of doing this also. So let's say we have a charged particle going this way, and we have magnetic field lines going this way. So assume here magnetic field is like uniform going this way. So in order to find out which way the force would be going, we'll have to use right hand rule. This is how you do this. 4 fingers, you have to use right hand. 4 fingers will be pointing along the B vector. The thumb will be pointing along the V vector. And if you put your right hand in this orientation, you will find your the force will be coming out of your palm. And it's not really the best orientation right now, so it's coming out of your palm over there. So that's going to be like this is right hand. The palm is below the drawing. It's not quite the best drawing, but we can try one more. Okay, so let me try one more at the bottom. So let's say particle is moving up, and it's always positive particles, and the field lines are going. Let's say field lines are going to the left like this. Okay, so you orient your hand so that 4 fingers follow the V. The thumb points along the V, and then here what we can do is we can draw just a dot. this was actually force, the dot. So the dot will be like, you look at the tip of the arrow. Now, if I were to draw it three-dimensionally, then I have to draw like a arrow kind of pointing outward. So to use your imagination. So if you position your right hand in this orientation, then the force will be coming out of your palm. Okay. So what this means is that like all those movies, if you watch those what's it called, action movies with the superheroes, like what's the guy, Iron Man, right? And we have Jedi, whatever. They always like point. You always use their palm, so right hand, and then the force comes out of the hands, like right hand usually. Okay. So that could be coincidental, but it's kind of related to what we're doing. So the force comes out of the palm of the right hand. Are there any questions? If it was a negative particle, so if it's a negative particle, then you can do one of the two things. You can either use left-hand rule, which does exist, but again, it's not as popular as the right-hand rule. Or you can say the force will come out of the back of the palm, so it'll be in opposite direction. So let's try it actually. So let's see. Let's say we have an electron flying this way, and let me now try magnetic field lines, which will be going into the page. So basically imagine that we're shooting arrows into the page, and all we can see is the tails of these arrows. So this is a magnetic field pointing into the page, okay? And velocity of the electron is to the right. So what we do is we point. So we can use the left hand. You point 4 fingers into the page, right? And you point the thumb along the V vector. Then you discover that the force on the electron in this field will be pointed down. Or if you use your right hand, again, you point 4 fingers into the page. The thumb goes along the V, and the back of your palm will be pointing down the page. Okay, how do you guys feel about this? Does that make sense? Makes sense. Okay, so let's try now to run some numbers, and if that makes sense, then we're gonna wrap it up. And I'll probably send you a small assignment on Monday. I'll probably give you a little quiz on the previous material, like not magnetic fields, like electric current. It will not be graded. It will not affect your grade. I just want to see how this will run on like online quiz. And in a week, we'll probably be back to like normal, classes, even though they will be online. So I'll give you like a test that was supposed to happen last week. It will be online test, okay, with a limited amount of time. And once the window closes, you cannot answer more questions. So that's going to be, yeah, we're going to go back to reality, okay? But it's like a week from now, so don't feel too bad. Yeah, I'm sure all will do really well, especially it's a virtual thing. Okay, you can cry later. It's okay. Cry later privately. You don't have to cry in public. Okay, let's try some numbers. Okay, let's try some numbers. Okay, so let's say we have an electron flying an electron. So the elementary charge will be 1.6, and this will be, well, let's start with a proton. It will be proton, and let's say it's flying at the speed of 100,000 meters per second. And let's say we have magnetic field of strength of 0.5 Tesla. So assuming that the velocity is perpendicular to the B, right? So by default, we should assume the angle between them will be 90 degrees. Then we can say we can calculate the force. So if you can quickly run the numbers and calculate the Lorentz force. So any volunteers, answers? This is Coulomb, by the way. You can either say it if you want to say it out loud, or you can just put it in the chat box. So let's see. So in the attendance, I got 29 responses. In the room, we have 31 people. So assume some people are from different periods. So the answer is 10 to negative 15, right? Okay, that's good. I see it's going to be 8, 10 to the negative 15 newtons. Now, this seems to be a really small force, but proton, the mass of a proton would be about 1.67 10 to the negative 27 kilograms. So if you quickly calculate the acceleration, you'll find that it's a pretty big number. So if you can, again, quickly run the numbers and approximate the acceleration. It's about 4.8, yes, 10 to the 12th. Okay, let's see that. It's about 4.8, roughly 10 to the 12 meters per second squared. So it's an enormous acceleration. Particles can experience enormous acceleration and they still intact. They don't get like destroyed. So one of the ideas that we had, like I had a long time ago, like if you watch movies when the like people travel in space, accelerate like really fast. Now, obviously, it's not sustainable for a human body. However, if you had a way to accelerate all the particles of a human body at once, then basically there's no limit at how fast you can accelerate, because all particles relative to each other will not be moving, and basically a person flying that kind of vehicle will experience zero, like feel sort of zero acceleration. Okay, we feel acceleration like if you're in a car on a roller coaster because different particles are moving at a different speed in different directions, and so different parts of the body experience different amounts of force. If every single atom in our body experiences exactly the same acceleration, exactly in the same direction, then you can accelerate as fast as you want. You won't feel any, you won't feel uncomfortable at all. Now, we got this, we got the force. I think we should start wrapping it up. Any questions? No question. Does anyone have like a bell schedule? If you can like send me a bell schedule. For the practice, I'm gonna post in Google Classroom a link and maybe a worksheet to practice. 26. Okay, so I think we're good then. Should we ignore Q, T? Yeah, we should ignore QE. So we're talking about like in the absence of electric field. Okay, thank you for the link. So we'll try to follow the bell schedule. I'll see you all on, today's Friday, right? Friday. Yay, Friday. I'll see you guys on Monday. Same time. Have a good weekend. Bye. Okay.